continue the next speaker, Shugailo Olena Oleksievna, Vasil Nazarovich Karazin, Kharkiv National University, talk about unruled affine submanifolds with two-dimensional base.
Hello, everyone. Thank you very much for having me at this conference. My topic is unruled affine submanifolds with two-dimensional base. Let's start with some definitions. We consider immersion F n-dimensional manifold into n plus m affine space. The choice of transversal distribution Q defines a torsion-free induced affine connection number from the decompositions on tangent and transversal components. The transversal components is affine fundamental form. For arbitrary transversal vector field Xi, we have the decomposition also on tangent and transversal components. And such we have definition of the shape operator and transversal connection. We can define the Weingarten mapping if we have more than one transversal vector. Yes, and for choosing transversal frame Xi1, so on Xi m, we have the affine analogous of the Gauss and Weingarten decompositions. We denote H alpha, it's component of affine fundamental form, S alpha, it's a component of Weingarten mapping or shape operators, and tau alpha beta is components of transversal connection. Why it's interesting to study ruled submanifolds? This type of submanifolds is representative of submanifolds with flat connection. If we have such affine immersion, so we can easily see that if affine fundamental form is 0, then F is n-dimensional affine subspace. If affine Weingarten mapping is 0, then we have a graph immersion. In general case, if Weingarten mapping and affine fundamental form is not 0, we obtain the following estimations concerning kernel of Weingarten mapping and affine fundamental form. If a kernel of affine fundamental form has a constant dimension, for example, L, then this submanifold is L-ruled affine submanifold. We have such a definition of generalized L-ruled affine submanifold with n minus L dimensional base. And we have such a regularity condition. If the directions, all directions, AI is constant vectors, then such submanifold is an affine cylinder with L-dimensional rulings. The simple case when the base of such a submanifold is a curve, it's defined earlier. And for such a submanifold, we define a natural parameterization and the natural transversal distribution. So we found its affine characteristic. There was that corresponding to directors of rectilinear generators coordinate tangent vectors belong to kernel Weingarten mapping and kernel curvature operator. We have such estimates for dimensional of kernel S, R, and H. Now we found conditions on the base curve and the directions of the rectilinear generator such that the induced connection is flat. In this a complete ruled affine submanifold with flat connection is not a graph and its connection is greater than 1, it's primitive rules false. It's not that if we have such a submanifold when it's phase with path connection, so it's just can be a cylinder. It's necessary to be a cylinder. Now we will consider affine rule submanifolds in affine space dimension n plus m with position vector. Such a way. And rho is a affine surface in m plus m affine space with transversal distribution psi1 is along psi m. And directions of rectilinear rulings were given by such vector. Here 1 is at the I plus m plus 2 coordinate place of a vector AI. If all of these vectors are constant, so we have a cylinder. It's not. If not, we have general case. So it's ruled affine submanifold. We can see from such a parameterization that if we take first derivative of AI, so it will be split. We have projection on the place and transversal space. So lambda and the projections. We can take sectors and here because of mixed derivatives are equal, we have such condition of integrability with position vector A. So let us assume that for affine surface rho, we have such affine as tau nabla, and we can substitute here decomposition of Gauss and Wingard. We have such a so here it's a decomposition, Gauss decomposition, and here Wingardian decomposition. Then we compare tangent and transversal so we obtain integrability conditions. But we need one more condition. It's condition of regularity, because we have vectors R1, R2, and these vectors are dependent rho1 and rho2, and these tricks, transformation matrix, must be non-generic for regular conditions. Here we can see that if all functions lambda and mu are 0, then we have cylinder. If functions mu are 0, then we have conditions on functions lambda. It's regularity conditions and integrability conditions. And in this case, the rules submanifolds will be ruled submanifolds in general, and its affine fundamental form will be will have dimension n minus 2. So all our rulings will be in kernel of affine fundamental form. So in this case, we don't have projections on psi, on transversal space. But not every base surface admits that the conditions is fulfilled, not for every base surface. I will say about it. And if, for example, we take all functions lambda are zero, so then regularity conditions is fulfilled, and then we have projections on transversal space and kernel of affine fundamental forms such immersion will be less than n minus 2, maybe even non-generate. We have very complicated regularity conditions, and in general case, it's too complicated to investigate these submanifolds as these immersions. So we can assume some more simple case of, for example, we can say that surface rho is a graph. It may be for any dimension m. Then integrability conditions is much simpler because we have flat connections and every vector psi alpha is constant. Comparing tangent components we obtain such components we obtain such equations for every alpha. In case if we want to construct ruled submanifolds with kernel of affine differential form, which includes all rulings, then we take rho is and we have such equality with function lambda. It's not be every lambda. It's depend on affine fundamental form. And as we know, we have regularity conditions also. Let's consider the simplest case when we have just one transversal vector, so we have hypersurface. And we know that in this case, surface is a two-dimensional surface in a three-dimensional space. So we have point classifications for such a surface. So we obtained such a result. If the point class of rho is hyperbolic, exists n minus 1 rule defines which with space rho and such that the dimension of kernel which is n minus 2. Here we have we assume that H is a affine fundamental form for fine ruled submanifold, not rho, but R. If the point class of rho is elliptic, n minus 2 ruled affine submanifold space rho such that dimensional affine fundamental form is equal to n minus 2 is a cylinder. If the point class of rho is parabolic, then we have two cases. Or they exist n minus 2 ruled affine submanifold. It's in case affine fundamental form of surface rho satisfies such condition, and it may be a cylinder if this condition is not satisfied. So H11 multiplied by H22 is not equal to 0. So we have not in just in this case for two-dimensional surfaces, So we have such a classification in case of codimension 2. So if we have affine immersion of two-dimensional manifold into four-dimensional affine space, so we have point classification for such surfaces. It was given by Borisenko and independently by Dicer and Marais. This does it means that we have three variant of points. If we can parameterize our surface and choose transversal frame such a way that H1 and H2 have such form, the point called elliptic. If we have such form, affine fundamental forms, the point called hyperbolic. And if we have such affine fundamental forms, so the point called parabolic. Obviously, if we have ruled affine submanifolds with affine rank 2, so it means we have affine fundamental forms rank 2, or in other words, the kernel of affine fundamental form has a dimension n-2. So in this case, point classification of affine rank 2 immersion pointwise dimension coincides with the point classification of affine immersions base surface. This theorem was obtained, but now we can look at this theorem in new point of view. If we have a complete smooth affine rank 2 immersion of pointwise potential 2 with the points of the same class, then hyperbolic submanifold is an affine cylinder with n-2 dimensional rulings over 2-dimensional hyperbolic base. An elliptic submanifold is a ruled submanifold with n-2 dimensional rulings over 2-dimensional elliptic base. So parabolic submanifold is or ruled submanifold with n-1 dimensional rulings over a curve, or a cylinder with n-2 dimensional rulings over 2-dimensional parabolic base. As we can see on this form of matrix of affine fundamental form, and this condition H11 multiplied here, H11 multiplied multiplied by H22 is less or equal 0. So we can see that for elliptic points, these conditions is fulfilled, and we can construct a ruled affine submanifold. This point is hyperbolic. This condition is not fulfilled, and it's impossible to construct a ruled affine submanifolds. It can be just a cylinder. Here we have condition in the third case. If point is parabolic, the affine fundamental form is in case A and case 2 is the same, but we can see that our condition integrability here it depends on connections too, and in different cases different relations between affine fundamental form and connection, we have two different cases. Of course, if we don't demand that affine fundamental form is maximal in this case, so not every rectilinear rulings belongs to kernel of affine fundamental form, then construct root affine submanifolds with any base. Because we can put here in this decomposition, we can put lambda, all functions lambda is 0 with conditions just on functions mu. And then it depends just on Weingarten mapping and transversal connection from this equation. So this approach is to study ruled affine submanifolds with different additional conditions. Obviously, we can't classify such submanifolds because there is no such a simple way to describe all two-dimensional surface. It's not a curve. We know if we have fine curvatures of a curve, so we have curve in affine space. For two-dimensional surface, it's not true. It's much more complicated, and we have much variety for our fine ruled submanifolds with such base. Thank you for your attention.
Thank you very much, Olena Alexeyevna.